Welcome to the session. I am Asad Jawahar. I am a software development manager on the Amazon Simple Workflow team. In this session, we are going to talk about Amazon Simple Workflow and how you can use it to build out various use cases in the applications that you build. And specifically, we are going to talk about the cron use case, which is running tasks on a periodic basis. I'm excited to have with me presenting today Jeff, who is one of our valued customers. And Jeff is the CTO and co-founder of Contactually. And Jeff is going to talk about how they are adopting Simple Workflow in Contactually, among other things, for their cron needs. So in this session, I'm not making any assumptions about any prior knowledge of Simple Workflow. So I'm going to give you an overview of Simple Workflow, and I'm going to talk about all the basic concepts that you need to understand for the rest of the content. So the overall flow is that we'll look at Simple Workflow, give you a brief overview. Then we will build out a use case where we might need cron-like functionality. And then Jeff will talk about how they are using Simple Workflow in Contactually. OK, so let's start with some basics. So what is Simple Workflow? In a nutshell, Simple Workflow is a service that provides the building blocks and a controller to reduce the complexity of infrastructure programming and state machinery. In other words, it's a service that makes it easy for you to coordinate tasks or work across distributed components of your application. So let me tell you a little bit of a history on Simple Workflow. So Simple Workflow was introduced as a public AWS service only last year. But really, within Amazon, we've been using it for a number of years in various applications. And the reason that we built Simple Workflow was to address a need that we saw becoming increasingly common in the types of applications that we were building within Amazon and the types of applications that we saw our customers try to build on AWS. And what was common in those applications was the way that they were getting their work done. And the way that they were getting their work done was by utilizing a number of different components that were running on a number of different machines. And the reason that these applications did that was either because they had some existing infrastructure that they wanted to reuse in new applications that they were building. And sometimes even the new components of these applications that the developers were writing from scratch were also running on separate machines. And usually they would do it because they wanted to have control on that component so they can selectively scale that out. And sometimes they simply wanted to reuse that component across many applications. So they made it into its own system, into its own service, then they were able to share across applications. And oftentimes, these applications were trying to model a process, or they were automating some process that was inherently distributed. So you can imagine a system where you may need to have a component that needs to run on a mobile device. Or you may have a component that is required to be run in a certain part of your network. So examples of these types of applications include things like infrastructure provisioning, which is the process of bringing online new servers, automation of billing processes, media ingestion, where you may have a library of videos that you process into different formats for consumption on different devices. Now, implementing these types of applications required significant investment in the infrastructure to coordinate work across these components. And this coordination involved creating tasks for these components, assigning tasks to these components. As these components worked on those tasks, monitoring their progress, keeping the overall state of the execution of the process somewhere centrally so that your application has one place it can look and tell authoritatively what's going on in the overall process. And this, all this infrastructure programming made these applications pretty complicated. And if you think about it, in reality, they were trying to do something very simple. So our goal with Simple Workflow was to provide this coordination infrastructure out of the box as a service so that you don't have to build it over and over again in your applications. So what Simple Workflow provides is a coordination engine in the cloud, along with libraries and tools that you can use to easily coordinate work across components of your application. And what that allows you to do is that it gives you the freedom, you, the application developer, to focus on the things that you care about, which is the logic the business logic, and the algorithms that make your applications unique. So a few use cases that we have seen our customers recently build on simple workflow. The first one here is NASA. NASA uses simple workflow for their Mars Curiosity project. And they use simple workflow to process the stereoscopic images that are being beamed down from the Mars surface. And those images go through a processing pipeline, and NASA is using simple workflow to orchestrate that entire process. And they are using resources both in the public cloud, in EC2, as well as some heavy metal machinery that they have in their own private networks. My second example here is Sage Bionetworks. Sage is a scientific research organization. They are using simple workflow to process very large genomics data sets using specific algorithms that various scientists are developing. And they're able to use simple workflow to share these algorithms across the community. My next example here is Fluid. Fluid was one of our customers that presented with us at reInvent last year. Fluid has a product visualization service. And what they do is they take images of products that their e-commerce customers want to present on their websites, and they create 3D renderings out of those images. And that, of course, requires a lot of processing, a lot of application of algorithms, and Fluid uses simple workflow to orchestrate that entire process. Fluid actually had an implementation which was not based on simple workflow, and for using that implementation, some of their more complex tasks required upwards of a day, sometimes 2 days, to completely process them. Using simple workflow, they were able to add a lot of parallelism in that process, and now they have brought down that time to process those images down to a few hours. So those are just some use cases. What we have provided with simple workflow is very basic foundational kind of capabilities, using which you can build a lot of different kinds of use cases, a lot of different kind of applications where you need to coordinate work across components. And one of those use cases that we are going to talk about today is cron. So what is cron? Cron is scheduled tasks. It's a facility that's available to you in the operating system. On the operating system, cron runs on a continuous basis, and you can configure that process to, say, run a specific task or a specific script on a schedule. Typically, it's used for maintenance and administrative types of tasks. So for example, you may have a script that kicks in every midnight, and it deletes some logs that your application is putting in a folder. Another application could be that you are generating a report every day, or you may have a script that backs up your database every few hours. So it's a general useful facility that you can use in a lot of different use cases. So if cron is available in the operating system, why might you build similar kind of functionality with simple workflow? Well, there are several good reasons for that. The first reason is that when you run cron on a single machine in the operating system, that single machine is your single point of failure in the system. If that machine goes down, then your cron is no longer running. Any jobs that you wanted to run on that machine are no longer running. The other problem with operating system provided cron is that when that machine is down, any tasks that were supposed to run during that time while it was down are lost. So if I bring that machine back up, or I replace that machine, it's going to start from that point on. It's not going to go back and backfill any of the tasks that were lost. With simple workflow, you have a lot of flexibility in how you handle failure conditions. So you can easily implement various mitigation strategies, and you can easily implement a strategy which says, if there was downtime, go back and backfill these tasks. The other obvious problem with running cron on a single machine is that that single machine is now your scale limit. If you wanted to run a lot of heavy-duty jobs on a periodic basis, you don't want to run it on a single machine. You want to run it on a pool of machines. But now that means you have to coordinate between those machines. And that's what simple workflow is built to do. And the last thing here is that sometimes operating system provided cron is simply not an option for you, especially if you're running in some sort of a shared hosting environment. Cron is typically not available as an option. So what you can do is that you can build those tasks as a simple workflow and still have them run on a periodic basis on these machines. So let's take a use case where we may need cron-like functionality and see how we can build that with simple workflow. So this is continuous integration, something we do in our development teams all the time. You have probably used similar systems or may have built similar systems. So the idea is that we have a number of developers working on a software project. And as they implement their components, they do incremental check-ins. And usually we rely on our developers to keep a high quality bar, but sometimes they'll check in code that isn't that great, and it breaks everybody else. So that's a problem. So what we wanted was to have a system that on a periodic basis syncs sources from our source repository, builds them, and runs a set of tests on those binaries. And then it sends out a report which says, a report on the health of our code base. So what that allows us to do is that if there's a bad check-in, we can go back and look at the last good build and then try to narrow down which check-in broke the build and try to fix that problem. So that seems like a fairly straightforward process. It's a script that you can implement using Ruby or Python or what have you. And there are 4 steps in this process, right? I sync the sources, I build them. When that process is done, I run some tests. When the tests have run, I publish the binaries, and then I send out an email which says whether the test passed or not. So fairly straightforward process. I can implement it as a script and run it on a machine with a schedule running through the operating system provided cron. But as I said before, that has several limitations. If that machine goes down, my continuous integration process isn't running. Any bad check-ins that happen, I won't know about this. The other problem is that this is my scale limit. If I had a lot of other software projects that I also wanted to run through this system, it will be a problem if I have continuous integration running on a single machine. So what I really want is that I want to have many machines running this job so I can scale them out. The other problem that I had with my script was that my script was a monolithic piece of code, right? And typically, I don't need to scale all parts of my application. In this kind of a situation, it's typically the testing that's the most resource intensive. So right now, I don't have any ability to dedicate resources, additional resources, just to the test piece. So what I really want is that I want to have my build tasks separate from my test tasks so that I can assign different resources to each of those tasks. And eventually, what I want is that if one of these machines is running a task and it goes down, I don't want to lose that job. I actually want another worker in my pool to pick up that job and keep working on it while I replace or fix that machine that went down. So my simple script now evolves into a little bit of a more elaborate application. And my application now has 3 components. I have 2 worker components. I have a worker machine that's doing all my build jobs. I have another worker machine that's running all my test jobs. And then I have this coordinator component. And the coordinator component is the component that's running the cron. And when it's time to kick off a build job, it's going to assign a task to the build worker to do the build. The build worker gets the sources, does the build, reports success back to my coordinator. And then the coordinator kicks off the test job, and so on and so forth. So one other thing that we wanted in our application is that we wanted it to be resilient to failures. So our coordinator component here is keeping its state in a separate little database on the side. Okay? So anytime a task is kicked off or anytime a task is completed, it updates state in that database. So there are a couple of very nice properties of the way that we have implemented this application. The first is that there's very clean separation of concerns. Each of my components is doing exactly one thing. Each of my workers, they only know how to do a build, or they only know how to do a test run. And they don't need to know anything else about what's happening in the system. Similarly, my coordinator component, it knows how the overall process works. So I can give it a job, and based on what's happened so far, it can tell me what are the next steps to be taken for that job. But it doesn't necessarily know how to do one specific job. The other nice thing in this application is that each of these components is completely stateless. So my workers here, all the information they need to do their tasks is provided to them as part of the task. So all they need to know is the build location or where to put the binaries. Similarly, my coordinator component, it is more stateful in that it needs to know the overall state of execution, but it's outsourcing it to a database, right? So what that means is that if any of these components goes down, I can easily replace it with a new machine, and it can get the state it needs from the system and recover. What that also means is that if I need to scale this application and run a lot of software projects through this system, I can easily add more machines and scale this application out. So let's now look at what that means in terms of simple workflow concepts. So the way that we implemented this application is very similar to how you implement workflows in simple workflow. There are a couple of basic concepts that you really need to understand in simple workflow to understand what it does. And those are decider and activity. So remember the coordinator component that we had in our application, which was the decision maker, the timekeeper. In simple workflow terminology, we call it the decider. And in simple workflow, when you implement a workflow, you implement a separate component which makes those decisions. And then everything else in your application becomes an activity. It's all the individual steps, the heavy lifting, the independent steps that happen, the units of work. So in our case, it was building the sources, running the tests, publishing results, and sending email. So when you build this process as a simple workflow and deploy it, there are a few more concepts that show up. So now I have these workers. I have workers both for my decider component, and I have workers for my activity components. A worker is simply a process that hosts your decider logic or your activity logic. And you can choose to have that process running on the same machine, or you can have them running on different machines. In this case, I have a separate pool of machines running my decider component and a separate pool of machines running my activities. Simple workflow acts as the glue between these components. Anytime my decider component needs to kick off a job or assign a job to a component, it asks simple workflow to create an activity task. Simple workflow assigns that activity task to one of your activity workers. The other thing simple workflow does is that it keeps state of the execution. So anytime it kicks off a task or anytime a task completes, it's going to keep a step-by-step detailed execution log. So remember our coordination component needed to keep state in a database to be resilient to failures. Simple workflow provides that functionality for you. Task is also the mechanism by which simple workflow communicates to your decider component. So anytime, let's say we kicked off the build job and that build job completes, your worker is going to report back to simple workflow that it's done doing that activity. Simple workflow is going to create a decision task to tell your decider component that you need to make more decisions. Your execution has moved forward, and it's an opportunity for it to make next set of decisions. One last thing remaining on that slide is task lists. So it's those small boxes that you see up in simple workflow. So task list is simply a collection of similar tasks. You can think of it as a queue. And what that allows us to do is to assign those set of tasks to a specific group of machines or to one specific worker. So in our case, we wanted our test tasks to be running on one set of machines and our build tasks to be running on a separate set of machines. So in simple workflow, I can create 2 separate task lists for that and have them assigned to different components. Okay, to quickly recap, key concepts in simple workflow. Decider, this is your decision-making logic. Activities, this is all the heavy lifting, the units of work that happen in your application. History, detailed execution log of what's happening in your workflow. And a task, which is an intent to do some work. So in terms of ownership, you own the step sequence logic. You basically own writing that decider component. This is your specific business logic. It's your secret sauce. You also own the discrete step logic, which are the activities. Again, this is your specific business logic. You also own the activity and the decider workers. And the nice thing in simple workflow is that you can host those workers anywhere you want. So you don't have to host them in EC2. If you want to host them behind a firewall, you can do that. The way that these workers talk to simple workflow is by using pull requests. So all you need is the ability for that worker to be able to make outbound calls to simple workflow, and then you can run that worker anywhere you want. And of course, you also own any data that goes into those workflows and the data that comes out of it. AWS and simple workflow provide everything else. So we provide the control engine, which creates these tasks, which assigns these tasks, and holds tasks while they're pending. Simple workflow also keeps track of the tasks as they're ongoing, and you can put time limits on how long those tasks can execute. It, of course, maintains the distributed execution history, and it also provides features that help you with operational tasks. So you can walk up to the simple workflow console, drill down into individual workflows that are running, look at, at the event level, look at the history, and that's very useful for things like debugging or journal auditing. So how do we implement our cron process using simple workflow? And a lot of it won't make sense right now, but in the rest of the presentation, we are going to drill down into details. But I wanted to show you quickly, what it looks like to implement a very simple cron workflow using Ruby on top of simple workflow. For all intents and purposes, you can think of the rest of this code as configuration settings that you're passing to simple workflow, and you inject your logic in these two blocks. The decider here is simply creating a timer to fire every day. When that timer fires, it kicks off a build job, and it's doing that in a loop. And my activity is simply a method. And really, I can put any Ruby code that I want within that method, and it will be executed as a task on a remote component. So if I already had a build script that knows how to do a build, I can simply invoke that build script from that activity method. And now I can run that method on many machines and load balance it. Okay, so we're going to go into more details and look at the individual pieces of the code that I'm showing here. But first, let's talk about the AWS Flow Framework. So the code that you just saw up there was implemented using the AWS Flow Framework. When we initially launched Simple Workflow, we introduced AWS Flow Framework in Java. And today, we are announcing similar capability for our Ruby customers. The Flow Framework is an ease-of-use library on top of Simple Workflow APIs. So just like any other AWS service, you can use Simple Workflow through HTTP calls. Next layer of abstraction on top of that is the AWS SDKs, which make it very easy for you to call our APIs from any language of your choice. And then what Simple Workflow does, a little bit unique, is that it also provides this ease-of-use library. And what it does is that it hides the details of our APIs and makes it very natural for you to program against Simple Workflow in Ruby. So it's built using standard Ruby constructs, and it allows you to use standard Ruby constructs to talk to Simple Workflow. We package it as gems, so you can easily deploy to any environment. And right now, we are in private beta, which is invitation only. The journal availability is coming soon. Stay tuned for that. Once it becomes generally available, it will be an open source project on GitHub. You can look at the source. You can contribute to it, just like you can today with Java Flow. Okay, so what are some of the benefits of using the Flow Framework? So Flow Framework makes it very simple for you to take existing code and wrap that into workflows so that you can run it on multiple machines and have it load balanced. The example that we just saw, where I had a build script already and I wrapped it in a simple activity, is an example of how you can easily do that. The other thing that the Flow Framework allows you to do is that it allows you to easily take advantage of Simple Workflow and do things like remote calls, do things like long-running operations, and asynchronous operations using Amazon Simple Workflow. And since it's an abstraction layer on top of the SDK, you don't have to deal with a lot of the API calls that happen under the cover. So remember how our decider component needed to look at the execution history and based on that make decisions? Simple Workflow handles that the Flow Framework handles that for you. So it, under the covers, makes call to Simple Workflow, gets the history, and based on that, it's going to invoke the appropriate code in your workflow to move the execution forward. And you simply program your workflows as classes and as method calls. The other nice thing in the Flow Framework is that failure handling is built in. Anytime you're doing distributed computations, there could be errors that happen on remote components. What Flow Framework allows you to do is that it allows you to handle those errors as if they were local errors. So you can use your standard error handling mechanisms to handle errors that may happen on remote components. And it also allows you to implement various kinds of mitigation strategies. So things like retries, they are built into the Flow Framework. And the other nice thing about the Flow Framework is that you can easily evolve your logic, right? Since you are not maintaining state, and you are not maintaining the events, handling the individual events that happen to modify that state, the Flow framework is doing it for you. Adding additional logic doesn't complicate that state machine. The Flow framework handles that state machine for you, and if you need to add one additional step in your process, you simply invoke another method call. So just to go over some of the constructs that we provide in simple workflow. So for failure handling, you use the standard begin, rescue, ensure blocks. We have extended this construct to work for both synchronous local invocations and also for remote activities that may be running on different machines. And if an exception happens in an activity on a remote component, we augment the exception stack with stack information from that remote component so that it's very easy for you to debug and see what went wrong. If you wanted to retry steps that fail in your workflow, we provide a declarative mechanism for specifying an exponential retry policy. And what that does is that you can declaratively say, if this step fails, let's say retry it 3 times. But when you retry it, wait 10 seconds before you do the first try, and then wait more time if it continues to fail. And that's very simple to do in using the AWS Flow Framework. We also add support for doing concurrent steps. So for example, you can imagine an application that needs to start a bunch of tasks in parallel and let them run. And at some point later in the execution, you want to get the results back and join them. Using the Flow framework, you can easily do that. We provide a send async method, just like you have the send method in Ruby. What this does is that it creates a task which runs on a fiber. And if it blocks, another task could be running at the same time. Send async returns a future back to you. So let's say if you had a bunch of those futures, at some point later in your execution, you can wait on those futures to collect the results of those parallel tasks. And since we are talking to remote components, we have to put bits on the wire. When you're programming your workflows in Ruby Flow, you program them in terms of Ruby objects. And when we put them on the wire, we automatically convert them using an extensible data conversion layer. By default, we support the YAML format, but this is totally extensible. You can go and add your own formats if you want. Some of our customers do things like encryption, or they do compression. We also provide an ability for your workflows to handle external events. So a good example of that is you have an order processing workflow where a customer decides to change an order. You can implement that as another method, which is marked as an interrupt point in your workflow. When that event happens, we'll invoke that method, and then you can handle it as appropriate for your process. And then the last thing I want to call out here is timers. You can think of timers as durable timers. So these are timers that you run in the cloud. So for our cron example, this is something that we will use quite heavily. OK, so what do we need to build for our continuous integration? We need to build a decider component. We need to build our activities. And then we need to build the workers for our activities and the decider. So quick recap of what our decision logic looks like. So our decision logic is basically a loop. We do the build step. Once that step is complete, we do testing. Then we publish the binaries. And one other thing that I want to add here is retries. If any of those steps fail, I want to be able to retry them up to 3 times. And I keep doing that on a schedule in a loop. OK, so let's look at the decider component. So using Ruby Flow, you implement your decider component as a class. In this case, I'm calling it the build workflow. And you extend this module called workflows. And what that does is that it brings into scope a number of utility methods that you need to implement the rest of your decider. One of those methods is the entry point method. And what the entry point method does is that it tells the Flow framework, when a workflow of this type starts, this is where the execution should initiate. So this is the entry point of your workflow. And the start method, which is the entry point, itself is just a Ruby method. And you can put any kind of logic that you want to put in there. In our case, the start method is taking 2 parameters, and those become the input to your workflow. In this case, I'm taking the location of the sources, and I'm also taking the location where I want to put the binaries when the build is done. The actual code here is a while loop that runs forever and keeps scheduling jobs after every hour. Okay. One other piece here is this activity client method. And what that is doing is that it's creating a client that I use to initiate activity tasks. So remember, those activities could be running on remote components, so it's not actually a local call. So this activity client is what I use to initiate tasks for that component to process. And I simply specify the class which implements them, and then I can use that activity client. So this is the actual implementation or the logic. So it's basically just running the steps in sequence. It's going to do the build, then the test, and then publish the results. So these are, it's a strict sequence. So the first task happens first. When it completes, then it will kick off the second job, and so on and so forth. As you can see, I'm using begin ensure here to do error handling. So if any of the tasks like build or test or publish fails for some reason, there's an exception, I simply bail out. I send an email and continue processing for the next hour. So remember that those are running on remote components, but here I'm handling them as if they were local. So one thing that was missing in our decider implementation is that I wanted to actually send those tasks to specific workers. And in simple workflow, you do that through task lists. And in the Flow framework, you can configure your task list on the client. And I'm showing a couple of variations of how you do that. So on the client, I can call the configure method, specify the activities, and then specify in a hash the task list that I want to use for those tasks. And another variation is that I can actually specify it on one specific invocation of an activity. So it's different levels that you can specify those task lists. And of course, I wanted to do some sort of retries if any of these activities fail. So the exponential retry, that the way it's exposed in the Flow framework, couple of variations of that. So first, we provide this retry block. And you can think of it as a block of code, a chunk of code, that if anything fails in that, if anything throws in that code, I want to apply a retry policy on the entire block. So I want to execute it from the start all over again. In this case, I only have one method call here, but you can imagine it could be any number of method calls. And the policy that I specify here is right now I'm only specifying how many times I want to retry, but this can get pretty elaborate. I can specify what specific types of exceptions I want to retry on, or how many times I want each exception type to be retried, and so on and so forth. In the second case, I am just specifying a retry policy on one specific activity. And I do that through this option block that's passed to the activity when I invoke it on the client. And my activities themselves are fairly straightforward. It's just a method call, and I can have any sort of logic that I want to put in there. It's really your business logic that goes in here. What's interesting here is the configuration that we specify on the activity. So remember I said that you can put time bounds on the computations that you do. So various different timeouts that you can specify on the activity. So you have the schedule to start timeout, which specifies how long can a task sit in a task list, waiting for a worker to pick it up. Then you have the start to close timeout, which is that when a worker actually picks up that task, how long do I want to wait for that worker to complete it? Then you have the schedule to close timeout, which is the overall total time from the point that I scheduled that task to the point that it's completed. And then I have heartbeat timeout, which is if I had a long-running task, I may want the activity worker to keep reporting that it's working on that task. So what these timeouts allow me to do is that if a worker dies, then simple workflow will realize that a task is timed out, or it will realize that your worker is not sending a heartbeat, and it will create a decision task and let your decider know that something's gone wrong, and then you can implement a mitigation strategy, like you can retry that task on a different worker, for example. The other configuration we have here is a task list. So remember, I was setting a task list when I invoked activities. If you don't have a use case where you need to route tasks to specific workers, you can just specify a default here, and then you don't have to specify it when you actually invoke that activity. And then there's a version which just tells you it's metadata in terms of my implementation. So one last piece for our decider. So this is a cron workflow, which is going to run potentially forever, right? It's a continuous process. So simple workflow is maintaining this history, and anytime there's an event in my execution, simple workflow is going to add events to this history that it's maintaining. Now that means if my process keeps on running forever, then that history keeps on becoming larger and larger. And since my decider needs to look at the history to decide on what to do next, it could become a problem because the latency will keep on increasing. I'll keep on downloading bigger histories. So a feature that's available in the Flow framework and simple workflow is called continue as new. And what that does is that in a single atomic step, it closes the current execution, and then it starts a new one with the same identifier. And your execution starts with a fresh history. So your history goes back to 0. So in this case, what I'm doing here is that I do 100 iterations of my continuous integration within the same execution. And after the 100th execution, I do continue as new, which is going to close this execution, start a new one, and my process will keep on running. So the last couple of pieces we need to implement. We need to implement the activity worker. The activity worker is the process that's going to poll simple workflow, ask for tasks, and then it's going to dispatch it to your activity method that you implemented. In the Flow framework, the activity worker utilizes 2 separate pools of processes. So it has a pool of processes that actually does the polling, and then it has a larger pool of processes that actually perform those tasks. So you can have a large set of tasks going on in parallel in each activity worker. And in order to create the activity worker, I simply pass it the simple workflow client, which is really configuration in terms of which endpoint you want to hit your credentials. You specify the domain, which is just a sandbox within simple workflow. You specify the task list from where to get the task, and then you specify the class which has your activity implementations. And then you simply call start on it, and it keeps on polling simple workflow in a loop. Same thing for the decider worker. The only difference here is that your decider worker utilizes a single pool of processes, uses the same process to poll and process the task. And we do that because your decider is supposed to be pretty lightweight. It's outsourcing all the heavy lifting to the activities. Similar configuration for creating the workflow or the decider worker, and you simply call start on it. So if you look at our documentation, we use the word decider and workflow interchangeably. So just to clarify, hopefully that doesn't cause any confusion here. OK, so once we have built this workflow, let's see how it runs in simple workflow. So let's start with the different actors that we have. So we have our decider worker, we have our build worker, and then we have our test worker. And let's just say that our test worker is running behind a firewall. Then I have the 3 task lists. I have the build task list, I have the test task list, and I have a task list for my decision tasks. So what happens when when I bring online these workers, they're going to start long polling simple workflow for tasks. And then I go and start an execution of this cron workflow. The first thing simple workflow does is that it creates an execution history for this workflow. And the first record in there is going to indicate whatever inputs I passed in to that workflow. And simple workflow is going to create a decision task. Decision task is dispatched to my decider. Decider looks at the history and sees it's a new workflow. So the first thing it does, it creates the timer. Simple workflow starts the timer. It keeps waiting for the timer to fire. When the timer fires, it updates the history, assigns a task to the decider, and the decider will then schedule the first task, which is to build. That task goes through the build task list, is picked up by the build worker. The build worker does the build and reports results back to simple workflow. Simple workflow updates the history, creates another decision task, and this time the decider schedules the test task. This one goes to our test worker, which does the test, returns the results. Simple workflow updates history, creates another decision task, and this time we will schedule a task to publish the binaries. It's picked up by our build worker, which publishes the binaries. And then the decider decides to send an email. Again, that's picked up by our build worker, which sends an email. And now one iteration of this process is complete. So the next time when a decision task is created, our decider is going to create the timer again, and the loop continues. Okay, so now I'm going to invite Jeff to talk about how they are using simple workflow in Contactually.
So, okay, so thanks, Assad. My name is Jeff Carbonella. I'm the CTO and co-founder of Contactually. So, Contactually is a contact management system that focuses on relationships. So, we try to enable our users, both individuals and teams, to harness the power of their network and relationships without spending hours each day manually entering data into a database. So, to accomplish this goal, we do a lot behind the scenes. So we allow users to connect multiple email accounts, social media accounts, CRMs like Salesforce, HiRise, contact management systems like MailChimp. And we pull in all this data and try to give our users a real-time view of what's going on in their network with their contacts and like their relationships. So for instance, when the last time they talked to a specific person was, what they talked about, any updated information like a new phone number or a job change. And so none of these systems really provide webhooks or feeds to subscribe to in order to get this change data. So what we wound up doing was polling each service every few minutes to try to get the most up-to-date data. Now, when we only had a handful of users, this really wasn't that big of a deal. But as we add more and more users, we have tens of thousands of accounts now. Scaling our cron is becoming a bit of an issue. So Contactually right now is a Rails application. It's running on Heroku. We use Rescue, which is a Redis-backed queue management system to manage our backend queues. And we use Clockwork to manage our cron flow. So the problems with our current setup, the first one is that the queues get backed up occasionally. And there's no easy way to dedupe jobs for a rescue. So cron will sort of mindlessly dump redundant jobs onto the queues, which just sort of exacerbates the issue. There's obviously the single point of failure issue, given that cron is running on a single instance. There's also no support for synchronous flows. So if you have anything, there's stuff that we would like to implement that with certain jobs follow in a certain order. And it's kind of hard to do, especially when everything's running in parallel. And lastly, there's poor tracking and auditing for generating reports to help our users sort of self-diagnose issues, which leads to more support headaches for us. So when we were looking for solutions to solve these problems, we also want to keep in mind that we didn't want to have to rewrite a lot of our back-end infrastructure. So Simple Workflow actually was actually a really good solution for us. So a simple workflow activity is pretty much just a rescue job. That's how we kind of associate it in our app. So a workflow groups relevant activities, allows you to execute them in serial, and it also allows you at each step to then do things in parallel. And I could, the example I'll show you in a second will kind of show you how that works. And then we have basically a cron workflow. It's sort of a parent workflow that calls the individual child workflows that are sort of the more function-based things that have specific steps that need to get done. So I'm going to quickly just go through and show you how we moved from our rescue setup to simple workflow, and just show you one of the main workflows that we migrated into simple workflow, and really only took probably a few hours to do. So if you look here, this is where we define the activity. So like I said, an activity is basically a one-to-one mapping of a rescue job. For those of you who aren't familiar, a rescue job is pretty much just a Ruby class that defines one method called perform, right? So you see here we have each activity is just calling the perform method of a rescue job. Now we have here's where we have a workflow. So this is the workflow that actually fetches new emails from a user's inbox and then processes those messages, creates any new contacts, and then it will generate a report actually based on that. So if you see, the first step there, we're using the retry block, so it'll retry that 3 times if it fails. You see on line 31, 32, it's actually processing all the emails that it found in parallel. So it's still maintaining order, but it's allowing us to still do some of our most time-consuming steps in parallel. And then at the bottom, the generate summary is actually something that we weren't really able to do given our current setup, because they're, aside from maintaining complicated state outside of rescue, there's really no easy way to go about doing that. And then this is our cron workflow. So you see here, basically, it just creates a timer. It sleeps for some amount of time. And then it enqueues a few workflows to be processed. And now the cool thing here is, if you look at line 28 there, you sort of get deduping for free. So with simple workflow, when you pass in explicitly a workflow ID, it will first check if that ID is already on the list and not processed yet. And if it is, it safely ignores it. And then, yeah, at the bottom here, line 32, we just do a continue as new, which will restart the history. So each time through the loop, we're actually generating a specific history block. So in our application, I guess the next piece I'll show you here is how we actually start the workers. So it's pretty simple. We just create a few rake tasks. So the first one starts the activity worker. And so these process all like the discrete logic steps that Asad was talking about earlier. And then the second task here starts the workflow worker. So basically, anytime a workflow gets added onto a list, this thing will pull it off and process it. And since we're running on Heroku, they basically have a process file. So you could define different process types. So when you push your code to Heroku, they'll start servers using these processes. And so you see here, we just pretty much commented out our clockwork and rescue processes, and then just added the simple workflow processes, and everything kind of just works. So that's it. That's how we implemented cron in our application using simple workflow.
Thanks, Jeff. So that pretty much brings us to the end of our presentation. So just to summarize, simple workflow is providing a foundational set of features that you can use to build a lot of different kinds of applications. Today we looked at how you can use it to build distributed cron. If you're interested to learn more, here are some resources for you to go check out. If you're interested in joining the private beta for the Ruby version of the Flow framework, email myself, asadj@amazon.com, or our product manager, sanjay@amazon.com. And thanks for taking the time to come and listen to our talk, and we'll take any questions.